learning coffee seminar again. So before we will start today's program, so a few words about the coming week. So unfortunately for the following 2 weeks, we won't have the machine learning coffee seminar, but then on the 10th of May, we will again continue with excellent presentations then. But there will be a 2 weeks spring break now at this time. But then for today's program, so I'm pleased to introduce you Dr. Yanhao Wang from the University of Helsinki, and he will be talking today about big data stream summarization. And then during the presentation, you are again welcome to ask questions in the chat, and I will then read them aloud. And then, of course, after the presentation, we will have a longer discussion then. But please, the floor is yours, Yanhao.
Hello, everyone. Today, I will talk about big data stream summarization. First of all, I will give a brief introduction about data stream and the data stream summarization. First, in the big data era, data streams are generated by many real-world applications. For example, they are generated by social networks, financial data, and Internet of Things. To handle the data streams, there are 3 challenges, which are called 3V. The first is the volume. The volume of a data stream may be in TBs. And the second is the velocity. The velocity means the generation speed of a data stream may be several thousand items per second. And the third challenge is the variety. The data streams may consist of numerical data, graph data, text, images, videos, and so on. To process the data stream efficiently, a common method considered is to summarize the data stream into a smaller subset, such that the subset can be processed more efficiently. So we need data summarization techniques for data streams. The concept of data summarization is to select a representative subset of a small size out of a massive data set for further analysis tasks. To perform the data summarization task on data streams, compared with the traditional data summarization methods on offline data, the difference comes from the following 5 aspects. The first is, for data stream summarization, we need real-time online processing instead of offline processing. And the temporal context in the data stream is important for data stream summarization. But for the traditional data summarization tasks, the temporal context is only important for some certain applications. And for data stream summarization, the storage of the data is not feasible. And to perform data stream summarization, we typically only need approximate results instead of the accurate ones. Finally, the time and the space complexity of a summarization algorithm should be linear or sublinear to handle massive data streams. But in the traditional setting, linear or superlinear complexity is permitted if we want accurate results. I will focus on one major method for data stream summarization based on the concept of submodularity. Submodularity is an important concept in discrete optimization. Here, the discrete optimization means a class of optimization problems where the variables is restricted to be discrete, such as integers, sets, and graphs. Submodularity is a notion in discrete optimization, which is defined on a set function that maps a ground set to a real value. The notion of submodularity is based on the concept of marginal gain. which is the marginal utility increase in the function value of adding an element V into a set S. So the similarity captures the diminishing returns property of the marginal gain. If we add an element V into a big set S, it will cause into a smaller set S, it will cause a larger increase in the marginal gain than adding it to a smaller set. This can be illustrated by this example, the coverage function. We can see if we have more if we can have more elements in the set, the marginal gain of adding a new element will be smaller. And if we have less element, if I have fewer elements in the set, the marginal gain of adding a new element will be larger. Submodularity is a natural model for data summarization because it captures the notion of representativeness and informativeness in data summarization. Here I have several typical examples for data summarization via submodular maximization. The first example is the classic algorithm problem of maximum key coverage. Given a collection of n sets and an integer k, we try to find a subset S prime of sets such that the number of elements covered by the subset is maximized. Obviously, the function of here the objective function is the union of the selected subsets, and the function is submodular because of the property of coverage. Maximum key coverage is a natural model for data summarization. Here we can consider all pieces of information in the ground set as is modeled as the ground set, and each element is modeled by some pieces of information in the ground set. And our objective is to find a subset of key most informative elements from all sets. The second example for submodular maximization for data summarization via submodular maximization is exemplar clustering. We are given a data set V and a distance function D and an integer K. We try to find a subset of K centers such that the loss function, the cluster loss function is minimized. Here the cluster loss function is similar to the one used for k-meaning and the classic k-meaning and the k-means clustering. It is proven that here the objective function fs is submodular if we introduce an auxiliary element with 0. Here, compared with the classic k-meaning and the k-means clustering, we have two additional restrictions. The first is cluster centers must be selected from the ground set V, and the distance function D is not necessarily assumed to be a metric. The only requirement for the distance function it is non-negative. The third application is active set selection. Given a data set V and a kernel function and an integer. Here, the most commonly considered kernel function is the Gaussian kernel. The objective function is to find a size k subset to maximize the log of the determinant of the kernel function of the kernel kernel matrix. Here, the function fs is a measure of diversity of the selected subset. in classic machine models, such as Gaussian processes and determinantal point processes. The function fs here is also shown to be submodular. So the main topic of this talk is to perform data stream summarization via submodular maximization. And we will cover different streaming models, including both the insert-only stream model and the sliding window model. And we will consider different constraints for the summarization tasks, from the most simple kinetic constraints, which restrict the size of the subset to be at most k, to more complex NetSecond and Metroid constraints. Here, for the Metroid constraints, we consider the group fairness constraint as a special case. In the first, I will give a formal definition for the submodular maximization problem. We first consider the problem 1, to maximize a submodular function subject to a kinetic constraint. Here, we are given a data set V, a set function f defined on V, and an integer k. The objective is to maximize the submodular function fs subject to the kinetic of s is at most k. We also made some additional assumptions on f. First, f is normalized, which means that the function value of the empty set is 0, and f is monotone, which means if A is a subset of B, then the function value fa is less than or equal to B. Finally, we assume the value of s is provided by a value oracle. All these assumptions are common for existing studies on submodular maximization. The submodular maximization problem is proven to be NP-hard for many classes of functions. For example, all the functions in applications 1 to 3 are NP-hard. And we typically consider approximation algorithms for this problem, including the greedy algorithm, the local search algorithm, and the linear programming relaxation-based algorithms, and so on. The traditional algorithm for submodular maximization with the kinetic constraint is the greedy algorithm. Here, the greedy algorithm means it starts from an empty set and runs in k iterations. In each iteration, it adds the element with the maximum marginal gain to the current set and adds this element to the solution, and find the one with the maximum marginal gain also in the next iteration, and run the algorithm for k iterations to return a solution. The approximation ratio of this algorithm is proven to be 1 minus 1 over e, which is about 0.632, compared with the function value of the optimal solution. But the greedy algorithm can only be used for the offline model. When the elements arrive sequentially over time at the stream, the greedy algorithm cannot be used anymore, because to find the element with the maximum marginal gain at each iteration, it requires random access on the whole data set. So it cannot be used for streaming. A streaming algorithm must process any element when it arrives without storing the whole data set. It only permits only one pass over the data stream, and the time and the space complexity should be sublinear to the whole stream. But approximate solution with lower approximation ratios is permitted for data streaming. Here I first introduce the well-known safe streaming algorithm for submodular maximization with kinetic constraints in insert-only streams. The basic idea of the safe streaming algorithm is to initialize candidates, M candidates, starting from an empty set with different thresholds from tau 1 to tau m. Then for each arriving element in the stream and for each candidate solution, if the marginal gain of the arriving element is greater than or equal to the threshold for this candidate solution, then the current element is added to the solution. Otherwise, the element will not be added to the solution. After processing all elements in the stream, it will find the candidate solution with the maximum function value from all candidates and return this solution as the final solution returned by the streaming algorithm. The approximation factor of the safe streaming algorithm is 1/2 minus epsilon for an arbitrary small epsilon from 0 to 1. The number of candidates maintained by the safe streaming algorithm is O log k over epsilon. Here we can see if the epsilon is smaller, the approximation ratio is better, but more candidate solutions must be maintained. And if the value of the epsilon is larger, then fewer number of candidates will be maintained. So we can make a trade-off from the approximation ratio and the space and time complexity by adjusting the value of epsilon. In many data stream mining problems, recent data is more important than old data. So one practical problem is how to keep an up-to-date summary for recent data. In our data stream summarization problem, we often consider the sliding window model to represent the data recency in data summarization. Traditionally, there are two kinds of sliding window model. The first is the count-based sliding window model, which only maintains recent W elements as active elements, and the L elements are expired. And the second kind of sliding window model is the time-based sliding window model, in which case each element is associated with a timestamp, and the elements after the timestamp t, the current t minus the window size big T are active, and the previous elements are expired. To perform the data summarization task over sliding windows, we propose the histogram-based algorithm, which runs multiple safe streaming instances starting at different time over the stream. Here I used the main idea of the histogram-based algorithm for submodular maximization over sliding windows. We have several safe streaming instances, H1, H2, until HS over the stream, starting at a different time, and process the elements from the starting point to the up-to-date element as an insert-only stream. In this case, we transform the sliding window, the optimization problem over the sliding window. It transformed into optimization problem and insert-only instance of the optimization problem. Theoretically, such a transformation will lead to a lower approximation ratio of 1/3 minus epsilon instead of 1/2 minus epsilon. Next, I will introduce the NetSecond constraint for submodular maximization. The reason to introduce the NetSecond constraint is to model the case of the cost of selecting different elements are not identical, but the total budget is limited. For two typical examples to use the NetSecond constraint, the first one is extractive document summarization. We want to summarize a collection of documents by extracting some sentences from the document collection. Here, we limit the total length of the summary in words. So the cost of selecting a longer sentence must be larger than selecting a sentence with fewer words. And another example is budget allocation in advertising. Here, we try to find a set of advertisers on a social, something like a social platform for advertising. If we want to select an advertiser with more followers, the cost must be higher. And if we want to select an advertiser with fewer followers, the cost will be smaller, and we limit the total budget. So this is the considerations for using NetSecond constraint. The NetSecond constraint, the submodel maximization problem and the NetSecond constraint is similar to the original NetSecond problem. The difference is here the utility function is not a linear function. It is a monotone submodular function. Given a total budget B and a cost CV for each element V in the ground set, we will limit the total cost of the selected subset to be at most B, while maximize the utility function Fs of the selected subset. The algorithms for the second problem, submodel maximization and NetSecond constraints, is based on the general idea of to consider cost effectiveness instead of only the marginal gains. Here, the cost effectiveness means the marginal gain divided by the cost of an element. To adapt existing algorithms, like the greedy algorithm and the safe streaming algorithm for the case of NetSecond constraints, we will replace the corresponding part or maximize the marginal gain to be maximize the cost effectiveness of the selected item. In this way, existing algorithms for the NetSecond constraints, including the greedy algorithm, the safe streaming algorithm, and the histogram-based algorithm, can all be adapted to submodel maximization and the NetSecond constraints, but at the expense of a lower approximation ratios. For the greedy algorithm, the approximation ratio will be lower, lowered from 1 minus 1 over E to half of 1 minus 1 over E. For the safe streaming algorithm, the approximation ratio will be 1 over 3 minus epsilon. And for the histogram-based algorithm, the approximation ratio will be 1 over 6 minus epsilon. The third problem considered in this talk is the fair data summarization problem in data streams. First, we will say fairness is an important issue in data summarization because data-based decision-making has been used in many sensitive domains, such as banking, hiring, and criminal justice, and so on. The usage of data-based decision-making has brings the risk of biases. Machine algorithms may be biased with respect to some demographic attributes, such as gender and race. So we consider the fair data summarization problem which aims to obtain a fair summary that is balanced with regard to some sensitive attribute. We define the fairness constraint for the data summarization problem. We consider the ground set V or elements can be partitioned into L disjoint groups, V1 from V0, according to some sensitive attribute. And we require a fair solution as the data summary, as the fair data summary. Here, a subset, we consider the subset S is fair if and only if it contains a specific number of elements from each group. The concept of fairness constraint is a special case of a more general constraint called the Metroid constraint. Here, the concept of Metroid came from the notion of independence in set theory, which has three properties. The first one is the empty set is independent. And the second one is if S is a subset of T, then, so sorry, there are some mistake here. Here, if S is a subset of T, then if T is independent, then S is independent. Third one is for two sets S and T, where the size of S is greater than the size of T, then there exists some element V from S minus T such that T union the element V is still independent. And we have the third problem to maximize a submodel function subject to a Metroid constraint, which is aimed to maximize Fs and guarantee that S is independent. The fairness constraint can be seen as a special case of the Metroid constraint. Typical examples for the Metroid constraint. The most typical example is the uniform Metroid, which is exactly the kinetic constraint we have considered. And the partition Metroid is the direct sum of the several uniform Metroids. Here, the fairness constraint can be seen as a partition Metroid constraint. If it permits less than ki elements selected from group Vi. But since our function f is monotone, we can add some random elements from the underrepresented groups, such for ensuring the fairness. So in this case, a fairness constraint can be transformed into a partition Metroid constraint without affecting the any approximation results, any theoretical results. So we define the fair submodel maximization problem, which aims to maximize the function fs and guarantees the selected subset S must satisfy some fairness constraint, some group fairness constraint defined on the ground set V. We first have a fair offline algorithm for the fair submodel maximization problem. Here, we can use the greedy algorithm for the Metroid constraint, which also starts from an empty set SD. And in each iteration, it will find the element V, such that by adding V to SD, SD is still independent. And V will lead to the maximum marginal gain to SD. And here we find that we cannot add any element anymore. Because if we add an element, any more element to SG will not be independent. In this case, we retain SG. The approximation factor of the greedy algorithm for Metroid constraint is slightly lower than the one for the kinetic constraint, which is 1/2. And we can also propose a fair algorithm for the streaming setting, which is called the fair safe streaming algorithm. Here, the fair safe streaming algorithm is mostly similar to the safe streaming algorithm because it also maintains multiple candidate solutions with different thresholds. But the different part is it also maintains a buffer B to store the elements that can neither added to the candidate solutions nor safe to be discarded. After processing all elements in the stream for the fair safe streaming algorithm, it will reconsider the elements in the buffer for post-processing. It will try to add the elements in the buffer to the unfilled candidate solutions using the greedy algorithm. In this way, the approximation factor of the fair safe streaming algorithm will be 1/2 minus epsilon, the same as the one for kinetic constraints, if the buffer size is unlimited. But the approximation ratio will drop to 1/2k if the buffer size is limited and in the worst case. There is another streaming algorithm for the fair data summarization problem, which is called the stream local search algorithm. The main idea of the stream local search algorithm is also start from an empty set. For each arrival element V in the stream, we will add the element V into S. If after adding V to S, S is still independent. Otherwise, it will try to find an element V prime from S, such that if we add V to S and remove V prime from S, S is still independent. And the marginal gain of adding V to S is at least 2 times of excluding V prime from S. Finally, after the procedure performing the procedure for each element, then we retain the final solution S. The benefit of the new of the stream local search algorithm is that it always achieves a constant approximation ratio of 1/4 in any case, and it do not need to maintain a buffer. So the space complexity of the stream local search algorithm is smaller, but compared with the fair safe streaming algorithm, it will achieve a lower approximation factor. If where the approximation factor of the fair safe streaming algorithm is 1/2 minus epsilon, but the stream local search algorithm only achieve approximation factor of 1/4. So until here, I have introduced the main methods based on Submodel maximization for data stream summarization. Next, I will give a brief introduction for other methods for data stream summarization. The first method is call set for data streams. Here, the concept of call sets is a small weighted or unweighted subset which can be used as a proxy for the full data set. And for a given problem, the result on the core set can approximate that on the full data set with theoretical guarantees. For data streams, the core sets are updatable and mergeable. Here, the updatable means given a new element, we can incrementally update the core set. The mergeable means if we construct a core set for a stream A and another stream B, then we union the two core sets constructed for A and B. We get a new core set for A union B. This is the notion of mergeable for core sets. So the notion of core sets has been considered in many applications in data streams. From the most simple one, the concept of core sets comes from the notion of some geometric properties. So the core sets is first used for maintaining the geometric measures of a data stream, like the width, diameter, and minimum including bound. And because the geometric properties is closely related to the loss function of a clustering problem, so the notion of core sets can also be used for k-means, k-median, and k-center clustering. And they are also used for many kernel methods, like kernel regression and spot vector machine. Finally, the concept of core sets can also be used to maintain the data distribution of the underlying data set, including the density estimation and the kernel density estimation problem in data streams. Another important concept for data stream summarization is sketch. Here, the sketch means a compressed mapping of the full data set onto a data structure which is easy to update with new and changed streaming data. For a certain queries, the results obtained from a sketch can approximate the results on the full data set. And typically, the notion of sketch means some probabilistic data structure to maintain the results for such queries. The notion of sketches can also be used in many real-world applications. The first class of applications is to maintain some stream statistics, such as quantiles, the frequency of elements, and the heavy hitters in the stream. And the concept of sketches can also be used for matrix approximation, including singular value decomposition, low rank approximation, and so on. So finally, I will give some future directions to consider in data stream summarization. The first direction is non-submodular optimization. Submodularity plays a key role in discrete optimization. I think it does plays the role of convexity in continuous optimization. So we can say more data summarization problems are non-submodular rather than submodular. I mean, we have only a very restricted class of problems which are submodular, and all remaining problems are non-submodular. But data summarization problems beyond the submodularity is still largely unexplored yet. The first is some further considerations on fair data summarization. There have been an emerging concern in the fairness issue for data summarization. However, existing works are still quite limited. They are often defined on some demographic groups because the demographic properties are easy to model. and they only apply very simple models to capture the explicit fairness constraints. For example, they simply give a hard restrict on the number of elements in the data summary from each group. So in the future, a good direction may be to capture and eliminate implicit and underlying biases in the data set for data summarization. And second is, in these problems, we only need to use we usually need to use the demographic attribute of the data set. This will cause some concerns in privacy. So in the future, it may be good to consider privacy preserving methods for data summarization. And the third one is, in the existing works, we consider the group fairness in data summarization. But the objective of group fairness may conflict with another concept of fairness called individual fairness. For example, if we consider the problem of selecting a specific number of elements from each group, there are maybe more representative elements from our overrepresenting groups are missing, and some not representative element from underrepresenting group is included in the summary. This violates the concept of individual fairness, where we should treat each element equally. So a future consideration is to balance between group fairness and the individual fairness. And finally, the current works on fair data summarization is merely based on algorithmic designs, and how to apply them to real world social systems is still a problem. And the third direction is how to apply machine learning models for data summarization. Existing data summarization methods are unaware of data distributions. Their objective is to provide worst-case theoretical guarantees in adversary settings. But they do not consider the underlying distribution. So they may not be the best choice if for a specific data distribution. So we will consider how to use machine learning models for data summarization. The idea of using machine learning model for the data summarization comes from the fact that machine learning is known to be effective in many other data management tasks, like machine learning-based index and machine learning-based query optimization. The basic idea of using machine learning for this data management tasks is to capture the data distribution using some machine learning models. So, because data summarization is also distribution aware, it could be it's possible to design a more efficient and effective data summarization methods with machine learning advices on the data distribution. Here is a summary of the talk today. We talk about the problem of data stream summarization. We first focus on the main method for streaming data summarization via Submodular maximization. We talk about the insert-only streaming and starting window model, and the problem and the canality, NetSecond, and the Metroid constraints. We also briefly introduce other methods for data stream summarization, which are courses and sketches, and also give some possible future directions for this problem. Here is a list of my publications on this topic, and the other references used in this talk. Thank you.
Thank you, Yanhao, for the very interesting presentation. So we are almost at the end of our time, but we could have time for one quick question. So if there is any from the audience, you are available to just open the mic and ask.
Okay.
Well, okay, so if there's nothing from the audience, so then I will use the opportunity. So how error tolerant are the methods? So especially the sliding window for the streaming method. So what if the data is very erroneous? How much does it then distort the solution?
For the sliding window, the difference between the sliding window model and the insert only stream model is the sliding window model only considers the recent data.
Yeah.
And it will omit the old data in the stream. So it will best fit the case when the data is changes rapidly, and we only want to capture the recent trend in the data.
Yeah.
So the result will be quite different from the insert only model, because the pattern of the underlying data is evolving, and it only captures the recent pattern.
Okay. Thank you. So I think we are now at the end of the seminar, but again, thank you, Yanhao, for giving the presentation, and thank you for everyone for listening. And as said, so next time we will meet on the 10th of May. So have a good day.